So I think that maybe we can start from exercise from yesterday. So it was exercise number, I don't know, I think it was number 7, but it's exercise number 1 for today. So it was show that finiteness can be decided in X space. Of vases, of course, yes. So checking whether reachability is finite can be decided in exponential space. And actually I realized it's good that we do it now, because actually our Z-VAS construction also can help us in that. So maybe a hint. So this is connected with what Michał yesterday said. Hint is like that reachability set is infinite if and only if from source you can reach some vector u, and from vector u you can reach some vector u prime such that u prime is bigger than u. So this property we can get from the construction of decidability of finiteness. So of course, if you can reach such a pumping loop, you have infinite set. But on the other hand, if you can't reach something like that, then if you construct this reachability tree, you will realize your reachability set is finite. So now would be nice to have something like that. U at most doubly exponential. And u prime maybe also at most doubly exponential. Something like that, yes? Some, I don't give you like all the details of property which we want to prove, but sorry. But I think this is the direction where we should go. So a few minutes for thinking. So maybe it's better if we stop here for a moment and we do another exercise which would be helpful for that. Okay, so just stop for a moment. We'll come back to it. And I want to do the following exercise. Show that coverability problem in Z-vases is decidable, and in, I think this is in LP, but if you come with some algorithm which is X time, it's also fine. So let's think for a moment about that. Okay, so maybe some ideas about this exercise number 2. If you have some idea, then please go ahead.
So the first thing is it doesn't matter where we start. So we might as well start from the origin. And the thing is, we have to decide for each vector how many times it is applied to to that origin, and you want to know if like these numbers can be set in such a way that we get a point in ZD whose all coordinates are at least 0 and at least one of the coordinates is greater than 0.
I mean, so I guess that you have already like encoded in your problem that we can start in 0 and finish in 0. Yeah, so this, but not necessarily. So it's not necessary that one coordinate is bigger than 0. Yes, if I understood correctly. You can cover if you reach exactly target. It's still okay.
If I
coverability
so
problem.
never mind. So
maybe
it's
I
even easier. Yeah. So okay. So it's even easier. So
okay.
We have a source and a target then, and we can assume
But
that
you start
say
from
source
some...
is 0.
Yeah. Yeah. Anything. This is what you would consider. Yeah.
Yeah. And then, like if you write, like instead of the system of equations, you can write the system of inequalities that say this coordinate has to be at least q1, this coordinate has to be at least q2 after applying all the vectors, and so on and so on. And you'll get the inequalities instead of usual d equalities. But we've seen that inequalities are equivalent to equalities.
Exactly. So instead of writing total effect on first coordinate 0, you can write total effect on first coordinate is something bigger or equal to 0, which you can, which you can express, or one more time you can write the total effect is something, and this something should be non-negative. Okay, so this is just this can be solved exactly by the same technology as Z-bus reachability. Yeah, so solution exactly the same technique as reachability in Z-buses. Okay, so I think that maybe this can be helpful for solving exercise 1. So we are back to exercise 1. Okay. So just think, and if you have some idea, turn on the microphone and speak. Also, if you have any observations which can be helpful for others, just tell us. So maybe here is one hint. So we have shown that it's enough to check whether there are such vectors, u and u prime. And one hint is show that it's enough. Okay, so hint. It is enough to look for u prime, which is u, plus some elementary vector, ei. So just adding 1 in some coordinate. So why it's enough to have something like that? Sorry. Maybe I should say. Also, maybe it's not what I wanted to say. No, sorry. I will maybe ask a question. So if you already have some u, how to check in exponential space whether you can reach something bigger than yourself? So given u, question, does there exist, so is there u prime bigger than u, which is reachable? And show that this is in exponential space. So how?
In this case, we can just solve coverability for all the possible u b's, which is u plus 1 in a single dimension.
Exactly. So this is what I wanted to express. So solution, yeah. Ask whether you can cover, yes, I can cover u plus ei for some I. Exactly. So maybe next hint. So show that it's enough that S can cover some U, which can cover some U plus EI. But maybe it's nothing to show. Maybe just observe that it's enough to ask that not from S you don't have to reach U. It's enough that you cover some U, such that from this U you can cover U plus EI. Yeah? Because if from U you can do this loop, then from everything which is bigger you also can do this loop. So now we want to look for something like that. And if we would know, so the only challenge now is to show that U can be small. Because if you would know that U can be small, you can check both coverability tests in exponential space. So now how to show that U can be small? Maybe some hint to inspire some discussion. So if you would know that this path which starts in U and covers U plus EI, that there is some bound for that path, let's say double exponential. Would it help? So let's assume first that we know that this path has some bound on itself. And then what do we do? Do we have an idea what to do then?
Then we probably guess the path non-deterministically.
Yeah, but I mean, how to show that you can assume that there is such U which is not too big?
I mean, that's the problem.
So maybe I will make this. Do you want the hint, or you want to think for yourself for a moment? I will give you another like 3 minutes, such that you have at least one challenging task here. Okay, so I will give a hint here.
I may have a rough idea.
Okay,
I can try something. Well, if we would,
if I should know something, then please tell me.
well, if we could for a while drop the assumption that we are in positive numbers, so we just consider z-vas, then the problem of coverability of U plus EI would be easy. And there would be, from the Pottier lemma, an exponential path which satisfied. But then there is a problem that if we find some point which satisfies this condition, then since we have no positive coordinates anymore, then we could go below 0. But since we have this bound on the length of this path, we know that we cannot go below 0 on more than like something exponential. So this would mean that if our point would have coordinates which are sufficiently big, like more than this bound, then we would never go below 0 in this many steps. So this would mean that if we could find sufficiently large point, then we could use our ZVAS machinery and this would work.
Yeah, so in other words, if you have something like u plus ei, and here you have not too big coverability, or let's say reachability path, then you can put it down so that already here it will not how to say it? It will not go below 0. So when you are talking, I started doubting whether my solution is correct. Actually,
well, what I wanted to say is just that this this solution in ZVAS is like uniform, like this path we could apply at any point. And we have a bound on how harmful it could be, like how much it can exceed 0 on negatives. So then it is sufficient for us to find u which is farther from 0 than this bound. And in this case, we have a bound on how big this u is enough to be. Like we don't have to find u which is like many times exponential, because like single exponential, we know it will be enough.
Yes, but my doubt is that so if you have vector u, which is single exponential on all the coordinates, and then it can cover itself in ND, then it can cover itself also in ZD, therefore there is a short path. But if you have a vector u, which is big on some coordinates, but small on some coordinates, let's say it's here, and so maybe we can have a coverability path in ND, but then it implies we have a small coverability path in ZD, but maybe this coverability path in ZD goes below 0 on this coordinate on which our vector u is small. So yeah, so actually, I'm sorry, so maybe, so at the moment I don't see how to solve that. So I can tell you what I was thinking. So I wanted to say something like that. If there is some u such that you can cover u, and then from u you can cover u plus ei, then by using, so I wanted to do what you propose, essentially speaking, like something similar. Then from u you can cover u plus ei by some short path, which is at most exponential, because I wanted to say from u you cover u plus ei also in z, in integer VAS, therefore this path is not too long, it's at most exponential. But here is a gap because this path is covering in z, but not necessarily in n. But if I would have this, then I know that I can, this path is at most exponential, so the path doesn't drop too much below u. So I can shift this u to quite a small value. And then it's just enough to consider u with small values. So another approach to that would be, okay, don't consider this in ZVAS, but consider this in VAS. And then if you want to cover u plus ei from u, you would like to consider Rakov lemma, but Rakov needs assumption that u plus ei has a small norm. So length of a path is small with respect to the norm of that. Okay, so I'm sorry, I don't know at the moment how to solve it. So I would like to do one more exercise. And if any of you will find the solution, please send it to me, and then I will send the solution to you. And if I will find it, I will also send to you. And if not, then yeah, maybe it was helpful to see that. Yeah, maybe fact is even this fact is even not true, but I suspect it's true. So let's consider the last exercise. Show that when deciding whether linear system of linear equations has a solution is NP-hard. And okay, so maybe not now without hint, and in a minute I will give you a hint. So that's so do you have an idea from what to reduce?
Looks kind of like integer linear programming.
Oh yeah, this is this is interlinear programming. Okay, so
we can do like anything. Vertex
so I
cover,
hope that
maybe not.
What?
Maybe vertex cover.
Okay, maybe. So my suggestion is subset sum, but maybe you can do a reduction from something else. This would be interesting. Okay, but is it true that so if you are familiar with interlinear programming, what I showed you, for example, with Potier lemma, was it known for you or it's something new?
What lemma? Sorry.
This Potier lemma about small solutions. Okay, so at least something new. Good. So let's think about reduction either from subset sum or from something else which you have in mind. We will prolong maybe by 2 minutes.
So we want to like first of all, like say we're reducing from subset sum. So what we want to have some binary variables. We don't have that yet, so we'll have to design them. But we want to have some binary variables which correspond to the choice whether we want to take some objects to the bag or not.
So let's say that we have like numbers from S1 to Sk, and we have a number S, and we ask, can we choose a subset T of S such that, yeah, what? Union of T in T of T is yeah. Let's for fixing notation.
Yeah, so let's first assume we have access to binary variables.
Okay.
Maybe not. Maybe let's try to design binary variables first. So in order to design the binary variables, I will actually introduce two variables. So I want to have, like, say, a binary variable x1. So I will introduce binary integer variables x1 and y1. And I will bound them by x1 plus y1 equals 1.
moment. So you want to, let's say you want to introduce B a bit, and then you have X, let's say X and Y, auxiliary ones. And what do you do with them?
And I write an equation x plus y equals 1.
Exactly. And then you either have 0, 1 or 1, 0.
And then I imagine that the value of b is exactly x. So because it's either 0 or 1.
Yeah, okay.
So
you make
okay.
like bi, and then you have xi, yy.
Yeah, that's correct.
Okay.
So with binary variables in hand, it's now very easy because what I write is just something like S1 times B1 plus S2 times B2 plus so on equals S.
I will write even, yeah. So S1 times X1, let's say, yeah, the first binary variable plus that plus etc. plus SK, XK equals S. Exactly. This means I can take 1 or 0 times S1, 1 or 0 times S2, and so on, 1 or 0 times SK, and this should sum up to S. And indeed, this is a reduction from subset sum. Okay, so thank you very much for listening to that. And yeah, it was nice to give this lecture. I think we will probably, so there will be probably some tasks, but I'm not sure exactly how it will be managed. If I will learn how to solve this finiteness in X space, I will send you an email. I guess probably I will have some access to your emails. And yes, and if you have some feedback about this lecture, I will be also happy to listen for future talks. Okay, thank you very much. And okay, and bye.